Okay, before we actually go into this detail of this soil erosion prediction, we need to discuss something more about this mechanical soil erosion control and a continuation of that. This is we call this as in the next one is, apart from this mechanical soil erosion control, we also use another control for to stop and check erosion, like this. This is called vegetative control. The vegetative control. The vegetative controls are like this. I mean, you say, if you are just trying to observe a particularly a slope, particularly a barren slope, how it looks like. So, here, say here, if it is a slope like this, say here the slope is broken at places like this, the slopes that we generally observe here. What is this slope when it is completely denuded, completely barren? So this is barren slope. Barren slope means you don't have any large plants. You have small plants, shrubs, like structures, not even that. Mostly this barren slope you will find near this freshly exposed slopes, new dumped slopes, where there is practically no vegetative cover. In such cases, what we generally try to do is, we have also found talked about this earlier. What we do is, generally we try to spread some vegetative material on the surface of the slope, What are these vegetative materials? These vegetative materials, depending on the availability and the requirement, we generally spread vegetative material spreading of vegetative what are these vegetative materials? Mostly cut haze, fallen leaves, say wood cuttings, are generally spread all over the barren surface of the slope, So these they work, the material works as the buffer for the rain, buffer for the heavy rain, thereby substantially reducing the impact on the slope, though much depend on the quantity, of the vegetative material, they can the the effort can reduce the soil erosion by about 50% over a year, by about 50% over a year. So much depends on the vegetative material works as the buffer for the heavy rain, thereby substantially reducing the impact of the slope. Though much depend on the quantity of the vegetative material, the effort can reduce the soil erosion by about 50% over a year. So this is also another very standard technique. This is also a very standard technique of, is just in case, just to suggest you another important thing is that when we generally cut grasses, in our gardens or any other places, or collect leaves, they can be a very important resource. This can be very important resource, particularly in areas where there are very little vegetative growth. This vegetative growth and very little rainfall, this kind of material, if it is spread over a large surface area, they can substantially improve the quality of the soil over time, and not only that, can reduce erosion to a substantial amount over the years. So having to say all this thing, now we can see that this is how the erosion can be checked and controlled, and at the same time there is a necessity for, in most cases, for how much there should be required, how much vegetative control required, how much mechanical soil erosion control structures are required, can be found out with the prediction of soil erosion. So we are going back to the main topic of the class now, is the soil erosion prediction. As per the universal soil loss equation, and the experience and knowledge gained so far, as per the universal soil loss equation and the experience and knowledge gained so far, we can find out this soil erosion potential of a slope by an equation erosion potential of soil by following equation, which is known as universal soil loss equation, universal soil loss equation, USLE. Now according to this, E is equal to RKLSCB. This E is the amount of erosion amount of erosion in tons. Remember this, tons per acre per year. Per acre per year. So this can be this can be found out like this. How it is found out here? What are the factors here? See, R is called the rainfall factor. K is the soil erodibility factor. L is the length factor, this is slope length factor. S is the slope factor. Slope gradient factor. C is the vegetative factor or vegetation factor. Vegetation factor. And P is known as the mechanical erosion control factor. Mechanical erosion control factor. Okay. Now, if we just investigate, trying to understand this soil and the factors that you can see here, R is for the rainfall factor, K is the soil erodibility factor, L is the slope length factor, S is the slope gradient factor, and the C is the vegetation factor. Now, here one interesting, P is the mechanical soil erosion control factor. Now, what is interesting here to observe is how this equation has been constructed. The most important part of the equation is R and K. R and K. What it means is, this is basically R means this, given a given a type, that is amount of rainfall and duration, given a type of rainfall in a geographical area what will be the erosion potential? What will be the erosion potential under of a barren slope of what will be the erosion potential, that is erosion potential in terms of, I am coming back to this, erosion potential of a barren slope of no or gentle gradient having given structure, conductivity, and texture, hydraulic conductivity and texture in tons per acre per year. This is what is R. Rk signifies R and K both multiplied. R and K both multiplied signifies the given a type of maximum rainfall in geography, what will be the erosion potential of a barren slope having given structure, hydraulic conductivity and texture. I will come back to that again. So, what you are trying to do here is all this, if we just identify, if we just discuss A again, Rk, the value of Rk is essentially modified, being modified by LSCP. LSCP, what it means is like this. Suppose is the construction of the equation is like this. Say you have identified that in a particular area there is a gentle slope having a particular structure, hydraulic conductivity, and also say hydraulic conductivity or permeability, as you can explain, and texture. If you have done this, suppose this slope here, as you can see this slope. Now this slope, there, if this slope is increased, say here it is say about say 10 degrees, if this slope is increased to say 30 degrees, so erosion would increase here, essentially should increase for the same condition, right. Similarly, if you just think across this slope, if this width of the slope further also increases, if this width of the slope further increases, if it is increased on both sides, then its usual value here towards this, the erosion will also increase, isn't it. Now this is LS, the effect of L and S, length of the slope and width of the slope, all right. The steepness of the slope or length of the slope and steepness of the slope, okay, length of the slope and steepness of the slope, right. Then C is now, if we are using any vegetation factor, like if you are using say mulches, the haze, the cut haze or the paddy or whatever you are spreading on the soil, the erosion would come down, should come down. So we are using C as a factor, which if it is applicable on the slope, it would bring down the quantity of erosion. So C, and then finally is the P. P is the mechanical soil erosion control. So understandably, if there is a slope like this, and if there is a slope having a say having a diversion ditch or having a terrace or having a terrace like this or like this, say in such cases we can say that the erosion would be reduced, isn't it. So all these L, S, C, P are actually the factors which would be working as an operator on this value of Rk. This is the basic principle of this equation Rk, L, S, C, P. So we would start with Rk, the basic value. So basic value of the slope, and then if we are controlling the other factors like the length of the slope, the steepness of the slope, then the vegetative factor and the mechanical soil erosion control factors, then we can identify, you can predict what would be the soil loss in terms of tons per acre per year. This is also just to suggest only a linear analysis, that is across a line, that it only tries to understand. This is what it says is a tons per acre per year. So this is RKLSCP. Okay. Now this is the nature of the function, as I have said. So the steps are so find out R, determine K, and S. If vegetation factor is applicable, use C. If vegetation factor is applicable, use the value of C. Otherwise, when no vegetation factor, use the value of C is equal to 1. Okay. Similarly, if no mechanical is applied. Similarly, if no mechanical erosion control is applied, use the value of P is equal to 1, or if some erosion control is applied, you can write here also is C less than 1, use C less than 1. So, it is C less than 1, use this one is use C less than 1, this is C less than 1. So, let me explain this again. Find out R. R can be found out by the geographical location. There is nothing much to find out, from the meteorological data, from the geographical data you can find out R. Determine K. K is the basic property of the soil. K deals with the property of the soil, that can be determined. K, that has to be determined. Say, as you have found out for the texture, as you have found out for organic matter in soil, the K has to be found out. Know the effect of L and S. Length and slope should be known. Generally, as a parameter it is given. If the vegetation factor is applicable, use the value of C less than 1. If it is any kind of vegetative factor is used, that means some form of haze, some kind of mulches have been used, say then we will say that C would be less than 1. Otherwise, when no vegetation factor is used, use C is equal to 1. So, what is in effect happening here is this, see this E, this is the basic value RK that I have said. Okay. Now, if it is say LS, also you would find out LS. Now, suppose if C, we are using C is equal to less than 1 multiplied by P is equal to less than 1. So, what is happening here is we can say now that you can say that is in a particular value like this, say here the total erosion potential has been reduced because this one are less than 1. So, we would find, say if we find this value as this is a value, we call it as E1, E2, and this one is as RK, LS and CP, where C is equal to 1 and P is equal to 1, then we can very well say U1 being more than E2. Not very complex. Actually, what I am trying to say is, if you have made some mechanical soil erosion structure on the slope, then the value of P would be less than 1. Otherwise, if you have not done anything, then P is equal to 1. Okay. Similarly, if you have spread some haze, some vegetative material on the surface of the slope, then C would be less than 1, otherwise C would be equal to 1. When nothing has been done, C would be equal to 1. So, as you can see in slopes where this mechanical soil erosion control has been made, then some vegetative material also has been spread, the erosion potential has gone down from its earlier position. That is only it tries to suggest. Okay. Now, having to say this is the nature of the function that we have explained. This is what is the nature of the function, this is how it would work, this is how it has to be explained. The nature of the function has been explained to you. Having gone from here, having further developed from here, we can very well now discuss about, say each of those factors in greater detail. So, rainfall factor. Rainfall factor is obtained from the annual rainfall data and the frequency of the rainfall episodes. The episodes are rainfall intensity depends on, is a function of episodes are rainfall, there is a function of rainfall intensity and duration. And episodes are rainfall intensity and duration. This is called the episodes. So, what is episode means? It says say when it is drizzling for 2 hours, drizzling for 1 hour, heavy rainfall for 10 minutes, heavy low, very medium rainfall for 2 hours. Each of them have different effects on the soil surface. The rapidity has a great impact. The duration of this, where the duration also has an impact. At the same time, the rapidity, the intensity of the rainfall also is of great importance. Just to suggest, what is, just to suggest in cases like kinetic energy, this is the generally with the rainfall. The kinetic energy associated with the rainfall, with any rainfall, with the rainfall is can be given by an equation where it is generally an empirical equation, which is much used, what is 8.73 log 10 I, where I is the rainfall in millimeter per hour, and Ke can be in the form of a potential energy, which is in the form of kinetic energy. This can be, this is, I mean, the kinetic energy in terms of standard equations for kinetic energy that we can mv square, half mv square kind of this thing can be found out here. So this Ke is just for your interest, though we will not be able to, will not use this, but it's just for your information. Rainfall in millimeter per hour plus 11.87, 8.73 it should be, and in terms of, I think this is would be in joules. That is what we should use here. So this is kinetic energy can be known like this.
What is T?
Here, what is
T? 11.8.
11.87. Okay, 11.87. Okay. Now this, having said this, so here this rainfall intensity, the rainfall factors, the episodes, and the, as I have explained, the rainfall factor. See, generally for a country, according to map, rainfall factor isoerodents. Isoerodents is this, I mean, locations having similar rainfall factor. Similar rainfall factor. So if you just try to say how it is generally done is not done for India, is not still done, but how it is generally done is like this. So, if you can see this, how these isoerodents are made, say isoerodents are like this, say like this contour maps that we do, say something like this. Say if this is a high rainfall area, say this high rainfall areas, like say if we consider the northeast, then you have this Andaman Nicobars having higher rainfall. So, here you can see this is what is known as the isoerodents. This is how the isoerodents are made. So, this is how this, say for India, the isoerodents may be looking like this. So, here you can see these isoerodents forming like this. So, here in such cases the isoerodents, like say Andaman Nicobar, the isoerodents would be between say about, say isoerodent, say let us start it from 700 isoerodent. Here this is 600, this is say 550, this is say 450, this is 400, like this. This is how these isoerodents are made. So, depending on the rainfall, depending upon the rainfall areas, depending on the rainfalls that we generally observe here. So, in this Andaman Nicobar area, starting from here, so we are going towards the more towards the arid region, towards the west. Okay, this is how these isoerodents are made. So higher rainfall areas, so you can have another isoerodent like say about 800, like this. So, these isoerodents can be once these isoerodents are available, so we can find it like this. We can say there is say rainfall factor, say rainfall type. Okay, the rainfall type is say heavy, long and high intensity rainfall. It's not, rainfall is not required to be written. Heavy, and say there we will have a rainfall factor say of 800, right. Then heavy but low intensity rainfall, maybe medium to high intensity rainfall. So, you will have it is 700. So, like this, this is how this rainfall factor would be given. So, I will give you I will talk to you in the the tutorial class how this is to be found out. So, the basic principle is like this. So, then we would come to say intermittent and medium to high intensity rainfall. So, you have the value like say that the value that we have said is about 600. So, 600, 400 like this, 400 it can be finally say in some portion it can be even 200 or 10 or 100 like this. So, these are known as the isoerodents. These isoerodents are generally found out, and depending on that the value of the rainfall factor, can the rainfall factor values can be between 800 to say 200 for say 200 or say even 50, say 50 you can write 50 for Indian locations. Okay, so you have a high dispersion of rainfall in India. We have several areas which are always under drought. There are several areas where there are heavy rainfall. So, we have a wide variety of rainfall factor that is possible. This is how the rainfall factor is identified. This is how the rainfall factor is established. Okay. All right. Then comes this much is clear, isn't it? This is clear, somewhat clear. So, rainfall factor values are like this. I will give you during the tutorial class, I will give you more about this, how this rainfall type is generally found out. The basic principle is this: soil erodibility factor. Soil erodibility factor. This soil erodibility factor depends on these three properties of the soil. This is firstly is one part of the texture, and the function of texture, that is percent silt plus percent very fine sand. Percent silt plus very fine sand. You remember, in the soil classification that I said, the USDA, US Department of Agriculture's soil classification is somewhat different from the European and universal systems. You can see that there the percent silt and very fine sand. Function of texture, if you know this, and then we can also this, and also another is percent sand. And then goes to this from, and so this also is about the soil structure and permeability. Okay, and permeability, and also this is one thing I missed here: soil organic matter. Soil organic matter. So, soil organic matter, these are the things which play their role into the computation, in the calculation of this soil erodibility factor. Let me give you a brief example, how this soil erodibility factor can be found out here. Just see this. Just see this, this particularly soil erodibility nomograph K. For K we find out this is from a very standard reference, Wishmeyer and Smith prediction or predicting soil erosion losses, USDA Agricultural Handbook. You see here that if you just try to observe this, try to observe these values here. You see this part is percent very fine sand, percent silt. Can you read this? This can be, this is readable, very fine sand, very percent silt plus this. The percent sand would be about say about 5%. This one is 5%. This you have found out. These are experimental values. You have found out. So you find a plot where this plot cuts with this 65% line. So here is the point. Here is the point that you can find out. Can you see this? What we are trying to find out? We know what values we know. We need to know. The values that we need to know is percent silt and very fine sand. We know that. Also we know what is the percent sand we have. So the soil, the percent sand is the soil sand of size 0.1 to 2 mm. 0.1 to 2 mm percent sand we know. So if it is 65%, so it is talking about a very fine soil, mostly the very fine soil and having say 5% sand. Rest of the material would be clay and other gravels and things like that. So here you can see, so 65% and 7 plus 5%. Percentage organic matter in the soil. Percentage organic matter in the soil. What is the percentage organic matter in the soil? So the percentage organic matter in the soil we have found out say at 3%. Okay, 3%. So this value is where this is the dotted line where this one, if you run perpendicular, this parallel to this line, this one where it cuts. Okay. Then from here onwards this gives you the first approximate value of K. The first approximate value of K here you can very well find out it to be about 0.28, isn't it? 0.28, isn't it? This way you can find out. Now here try to say this. What these are experimental values that we have found out. Sand, silt, clay and organic matter, we know that. So from that we can have a fast approximation of the value of K. This K needs to be further refined. The value of K needs to be further refined. So what we do to further refine this value of this K, what we do is we generally run to the map for soil structure, which is given as 1, 2, 3, 4. 1 is given as very fine granular soil structure, fine granular, medium or coarse granular, blocky, platy or massive. So here our soil comes under fine granular. As you can see, most of the fines and silt constitute most of the soil. So this one is 2, this 2 here. So here it is getting connected here as this value of 2 here. It is connecting to this line of 2 soil structure, 2 soil structures 2. So here from there as we drop it down further we finally find out this permeability connect with the permeability value 654321. This 654321 values you can see the very slow slow to medium, medium to moderate, moderate to rapid. What should be this soil? Understanding from this soil, what we can find out is this soil should have a very slow, slow to moderate or quite slow permeability, because most of the constituents are silt and sand. So here this is where it connects here again, and at this point what is this one is basically the value of 4 permeability. The 4 permeability is nothing but here, as you can observe here, 4. This 4 when again brought back connected to this, we find the final soil erodibility factor, the final soil erodibility factor as 0.3. So what we started was with 0.28, we have refined the value to 0.3. So the value of K in the nomograph would be 0.3. So we have found out two values, R and K. ALASCP we will find out later in the class. So in the next day we will find out the value of ALASCP, and I'll show you about how for a soil we can determine the value of its soil erosion potential.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape, and IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range.
দেশের তারে খাচ্ছি সবে আমাদের গর্ব ভাই যোগ কর্ম সুকৌশলম যোগ কর্ম সুকৌশলম একে সিদ্ধে বর্ণ যোগ কর্ম সুকৌশলম आदर्शाय मादर्शाय प्राणदास्मह्मयम् योग कर्म सुकौशलम् योग कर्म सुकौशलम् योगा कर्म सुकौशलम्.
Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.